It gives me great pleasure to introduce our next speaker, Dr. Dewitt of Columbia. Dave is program manager of IRI for its climate program at IRI, which is part of Columbia University at the Lamont campus. He's also the program leader of the Dynamical Prediction Systems. Dave did his PhD from the University of Maryland, College Park, with Ed Schneider and Shukla. And his interests, as the title of the talk suggests, is about seasonal prediction, coupled models, and essentially dynamical models. Dave.
Thanks. So I wanted to thank, can you hear me? Is that okay? It's in the back? Okay, sorry. If I start to talk too fast, please yell at me. I'll try not to talk too fast. I think I'll probably go about an hour, but if we go long, I'll just put some stuff into the other talk tomorrow. So I definitely wanted to thank Amit and Ravi and Sulachana for inviting me to come speak and for sponsoring the trip here. I also want to thank Lisa Goddard, Randy Koster, and Andreas Vagel for letting me borrow a few slides. Basically, yes. Happy to give you my email if on the lecture notes or anything else. If you want to send me email, just please put in the title IIS. Or sorry, the name of the course. Sorry. Yeah. Okay, so this will be the outline for the talk. I'll just actually talk a little bit about the relationship of this to data assimilation. So I don't do data assimilation. I mean, I use data assimilation products. But the seasonal forecasting problem does use, as I say, quite a bit of data assimilation. And it's going to get more and more, and even in the things like climate change and decadal centennial forecasting, because people want to know more and more things, like how does carbon vary, how does aerosol vary, and to do that you really need to be injecting observations into the system, which you really need a data assimilation system to do. So I'll talk about some dominant mechanisms of the seasonal variability. ENSO, of course, is the one that you need to be able to predict if you want to have any chance of doing most seasonal forecasting problems. And so the dominant mathematical theory, or the simplest model that describes ENSO, is this thing called the delayed oscillator. From ENSO, you get these things which are called global teleconnections. I'll just show that. I mean, of course, here in India, you realize that you're affected by ENSO, but most of the rest of the world, up to the mid-latitudes and even the high latitude, is also affected. So another important factor, although much less important than ENSO, is soil moisture. I'll talk a little bit about that. So I'm not going to talk about this actually. I put this in originally. Just this is a hot topic right now, believe it or not, in seasonal forecasting, stratospheric, tropospheric, sorry, I misspelled this, connections, and so I'll just comment on that later. So I mean, when I was a graduate student and decades before that, if you said that the stratosphere had a significant impact on the troposphere, people would have said that you were crazy. But what people have shown is that actually under certain conditions of the basic state being the mean wind field, you can actually get downward propagating anomalies that last for a long time in the high latitudes. These are associated with things like the Arctic oscillation, if you've ever heard about that. So then I'll talk about two-tiered versus one-tiered forecast systems. So two-tiered would be an uncoupled, that would be just an atmospheric model. A one-tiered would be a coupled model. So the coupled models are a lot sexier. It has an atmosphere and ocean, has a lot more variability. It also has a lot more chance to have errors. So I'll talk a little bit about that. And at the end, I'll talk about, sorry, there's no 5, dynamical cores. So I'll talk about the most common dynamical core being used in the seasonal forecasting models is this thing called a spectral dynamical core. In the future, though, you're going to see a lot of people move to these finite volume dynamical cores. A very popular one is called Lin-Rude, and that's because of the conservation properties. And again, I'll go over these equations for the spectral method, and I'll repeat this later. Part of the reason that I'm going to do this, so you say, why do you want to talk about this if this is the future, is that someone mentioned the other day, I mean, these climate models evolve on timescales of 5 to 10 years, and so it's unlikely. For instance, NCEP has just come out with a new version of their CFS V2. That is a spectral global model. That model will probably not be replaced for at least 5 years, and so you'll have to know how to deal with spectral models for at least the near-term future. Okay, so here's my attempt at the relationship between these talks and data assimilation. I actually will show a little bit of results from some data assimilation tomorrow, not so much today. The seasonal forecast for the climate state need the data assimilation for at least 2 ways, right? So you need to specify the initial state of the ocean and the atmosphere. So it's really an asymmetric problem in seasonal forecasting, especially if you go out past, the first month. You're really dependent on what's the ocean initial state, not so much the atmosphere. People talked earlier today or yesterday, the Lorentzian limit of weather forecasting is 2 weeks. So beyond that, instead of it being an initial value problem, it's really a boundary value force problem. And so you really need the ocean. Other things are important. Land is secondary important. Ice is important, but the problem is that we don't do it very well. And so most people take a very simple approach to controlling the ice to keep it from going bad as opposed to actually trying to predict it. The other thing is that given the sparseness of the observed data in the ocean, not so much the atmosphere, although some parts in the tropics it's true, the data assimilation system acts as an estimate of the observed state to verify your solutions. Right? Of course, that's not without problems because different data assimilation products give very different answers in some places, especially in the presence of sparse data. And I'll show that, and that's becoming especially important in the decadal forecasting problem for things like temperatures at 500 meters and salinity at 500 meters where there's essentially, maybe 1 or 2 observations a year. So here I'll just offer this hypothesis again. So in order to construct an assimilation system, it's desirable to know something about the physical system and the models that represent it. And so I'll try to talk a little bit about these seasonal forecast models. And at times I'll try to introduce places where data assimilation is starting to grow. And in particular, I could stop now and say land data assimilation is becoming quite big. That's also a sparse problem. There's not a lot of soil moisture data. And the ocean assimilation problem, even though we've been working at it for arguably 15 or 20 years, is very primitive. Most of the ocean data assimilation systems are 3D VAR. For a long time they were univariate in temperature. Now they're usually multivariate temperature and salinity, and that's mostly because at the equator, if you don't also do salinity at the same time, you introduce vertical stability errors. There are people doing Kalman filter, coupled data assimilation. The GFDL group is doing that and getting some nice results. So you may see people evolve that way, but again, on a 5-year time scale sort of thing. Okay, so physical phenomena associated with seasonal climate variations. ENSO is dominant. For those of you who don't know, and I assume that this audience is kind of mixed. Some people have a background in meteorology. Some people have it in short term. Some people have it in seasonal. So I'll just go over everything. So SST variability in the Central and Eastern Pacific is what's called the El Nino part. The southern oscillation is the global manifestation of the response, usually looked at in the surface pressure field, indicated by the pressure difference between Tahiti and Darwin. And the thing about the ENSO is it forces global teleconnections because the convective heating, which is also known as rainfall, associated with that SST variability in the Central and Eastern Pacific, causes perturbations to the global angular momentum field, and it causes waves to be driven, Rossby waves that travel west for the most part in the stationary sense, at west and away from the equator. And there's also changes to the zonal mean circulation, things like the Hadley circulation. So the second thing is, again, this soil moisture anomalies. We talked about this, and I'm not going to talk about it anymore. So then the SST variability in other parts of the ocean, including things like the Indian Ocean dipole, is important. There's also an Atlantic meridional mode. The thing about this, which we'll get to in the second, so I'll get there. So sea ice variability, again, is important, but the problem there is that we don't do it very well. So ENSO is the dominant factor in the seasonal climate variations. It has this regular period of 3 to 5 years, so it's not a perfect oscillation, right? It has an oscillatory behavior, warm to cold usually. Cold doesn't necessarily go to warm. Cold usually fizzles out, and we'll talk about that in a minute. So it's also fortunate, that's the problem, that we can model the most skillfully. But most here is in quotes because there's a lot of room for improvement there. Tomorrow we'll talk a little bit about the fact that seasonal forecasting is a marginal skill problem. And so there's plenty of upside if we can get there. I think most people believe data assimilation would help us to do that. Okay, so how does ENSO work, right? So there's this first order model known as the delayed oscillator. This was formulated around 1988 by 2 groups independently, Paul Schopf and Max Suarez at Goddard Space Flight Center, and David Battisti and Anthony Hurst at the University of Washington. And so the model relies on the properties of equatorial ocean waves and the fast response of the tropical atmosphere to those SST anomalies. So you may have heard more recently, people will talk about things called the recharge oscillator. So recharge oscillator has the same basic mechanism. It's the waves, but the difference is how the mass from the Rossby waves, which we'll talk about in a second, gets back to the equator. And so the question, the difference between the recharge oscillator and the delayed oscillator is how important is the western boundary. If you talk to someone like Paul Schaff, he'll say that, of course, you're getting mass transfer the whole time the Rossby waves propagate to the west, but you still need the western boundary to bring enough mass in to get the phase change. So the main aspect of this is how to get the period and why it oscillates. So the key oceanic equatorial wave properties that we'll rely on for this, we're going to use for the most part first vertical mode equatorial waves, Kelvin waves, which travel east at about 2.8 meters per second along the equator. And these first equatorial mode, vertical mode equatorial Rossby waves, which travel at 1/3 that speed to the west. Now, I'll say, as you see when I get into this idealized example, the period will be too fast, and so the way that you adjust the period is if you go to a second vertical mode, these waves become slower, and also these waves, and also if you go to higher meridional modes, the Rossby waves also become slower, and the asymmetric Rossby waves are slower than this as well. There is only one meridional structure for the Kelvin wave. So equatorial Rossby waves will reflect at the western boundary as equatorial Kelvin waves. The equatorial Kelvin waves will reflect at the eastern boundary as equatorial Rossby waves and coastal Kelvin waves. And the coastal Kelvin waves are important, so if you ever look at global SST maps and see warming along the California and South American coast associated with El Nino, that's these coastal Kelvin waves spreading the signal away from the equator. And then another important consideration is that a westward wind stress anomaly produces a downwelling Kelvin wave and an upwelling Rossby wave, and the opposite is true as well. An eastward wind anomaly will produce an upwelling Kelvin wave and a downwelling Rossby wave. So the waves coming off the same signal propagate in different directions and have different characteristics with respect to upwelling. I'm sorry,
Use the word signal.
I don't remember. Is it on here, or which context did I use it?
The signal propagates along the...
Oh, okay, so the waves propagate.
Joe's talking about the waves.
Yeah, sorry.
Okay.
Is that okay?
Yeah.
Yeah. Okay, so this, I'll use an idealized ocean basin. This is the Pacific Ocean. This here is the coast of South America. This is Australia. This is a solid boundary, okay? And so some of the issues with this idealized domain is that this boundary is perfectly reflecting of the real Pacific. If you look, there are actually islands over here. Some people have shown that you still get pretty good reflection. Not everyone believes that's true. But anyway, this is the easiest way to do this in a nice, clean way. There's no mean currents here, and so I'll impose a zonal wind stress anomaly. Zonal wind stress anomaly. This will be westerly. Here's the color scale. So essentially, this is a wind blowing on the ocean along the equator this way. Okay, and so this is what it looks like if I slice through it. That's what the wind stress anomaly looks like. I did this numerically, not analytically, so I introduced a little bit of an error here, so it's not quite perfectly symmetric. And the wind stress curl anomaly is what drives the ocean upwelling and downwelling, especially next to the equator. It's actually a linear relationship. And so if I look at the wind stress curl through this, it looks like this again. There's a small error because of my sloppiness with the prescription. And this is what's going to force these vorticity anomalies, which will force these upwelling and downwelling anomalies. So when I do that, this is after a few days, this is a Kelvin wave that's moving out to the east. This is this first symmetric meridional Rossby modes, which are going to move to the west. This is downwelling. These are upwelling. This is a slice through the Kelvin wave. This is a slice through the packet of Rossby waves. So then at some time, 25 days later, these are propagated away from the thing, away from where I've initially prescribed it. And so what I've done here is I've just made a pulse, right? I haven't kept forcing. So again, this is just so that we can examine how these things propagate and how they reflect. So here by 50 days, remember it's moving at about 2.8 meters per second, this particular wave that I've chosen, it's impacted onto the western boundary and is starting to reflect as as coastal Kelvin waves. And it will then start to come into the interior. as that first symmetric Rossby mode. And you see this one again propagating to the west. Later still, propagating to the west, you see here that these waves from this impact have started also moving to the west. Yes? What's that? No, so the thing about this this particular set of waves is that they're equatorially trapped. Yeah, so it'll just propagate along this equatorial waveguide. Curl is the vorticity operation, essentially. So it's the vector curl operation. Does that make sense? So I take dv dx, or d tau x d tau y dx. Yes. But it's the curl of the wind. Yeah. Yes. But in the ocean, it's called the curl. Sorry, yeah. It's just a mathematical operation, right? It's okay? Right, so again, here's these waves reflecting back into the interior. These waves have started to impact on the western boundary, and again, this is time going forward. It's reflecting now back as a Kelvin wave along the equator. You can see that it starts to split this other signal. Coming back here, on the order of 275 days, it's changed the sign of the thermocline anomaly along the equator. So what does that look like in the real world? So this is actually a plot of temperature anomalies along the equator. This is 120 east to 80 west. This is depth. Red is positive, blue is negative. These are temperature anomalies. So if you look at Toga Tau anomalies, for instance, they look something like this. And so again, marching through time, here's 18 months, 6 months. You see that this signal will propagate from west to east. Then later, when you reach the peak warming, the opposite sign signal has appeared in the west and will propagate again to the east, replacing the warm signal with a cold signal. And then it just repeats itself. Again, this simple system. And what does that look like? So those were the things I was showing were sea surface height anomalies of vertically integrated temperature. This is the actual temperature. So what does temperature signal look like that's associated with that? So here you see it's confined along the equator, spreads along the South American coast. So the phase would go from cold to warm, intensifies in warm. Then again, you see that it will flip back to the cold again. So the real world manifestation of those waves looks like this. So again, this is about 18 months before a peak warming. You see this Rossby wave energy that's impacting on the west coast. You notice that it's not really symmetric. This is the residual signal from a Kelvin wave. This reflects as a packet of Kelvin waves, actually, both free and forced to the equator. This intensifies due to coupling, and again, we start to see the generation of more intense Rossby waves. Again, it's not symmetric here, reflecting at a non-uniform boundary here in the west, and it will come again eastward as this same wave type of structure, Kelvin wave type of structure, changing the phase. So what does that look like actually along the equator, and what's the connection with the wind stress? So the contours are the SST anomaly. This is actually during the peak of an El Nino anomaly. This is just a regression. Observed data, actually, again, it's not observed data. It's actually NCEP ocean reanalysis. You regress this against the other points in the domain. The Nino 3.4 index, which is the average from 5 north to 5 south over most of the eastern part of the Pacific Ocean. And so you see the temperature change that's associated with that, and you see that there's this wind change that's in phase with the temperature change. And what's happening is that these wind changes are continuing to drive more Kelvin waves to the east, reinforcing the temperature signal. Here's what the heat content anomaly looks like. Again, this propagation from west to east. But again, with a longer period than was shown in the idealized calculation, and we'll go over why that is. Right. So why is the period faster than what I was showing with that idealized calculation, which would have been about 2 years? So because the equatorial atmosphere responds to the SST anomalies very quickly, the wind stress response would keep amplifying that original signal. So the westerly anomaly that I imposed, once the SST anomaly started to come, it would continue to exist and continue to drive Kelvin waves to the east. If it were opposite sign, it would have opposite sign Kelvin waves. Yeah, so that's here. So what actually ends up changing the phase is these opposite sign Kelvin waves are going to be generated there at the central and western boundary, and they're going to keep being generated by this wind stress anomaly that's in equilibrium with the SST anomaly. The other thing is that the oscillation is irregular, with warm events usually followed closely by cold events, but not vice versa. So if there's an El Nino, you're almost guaranteed that there'll be a La Nina that follows it. If there's a La Nina, you know, it'll usually actually just fizzle out, or it'll actually come into a second weaker La Nina. And again, this comes back to the earlier argument. The lower order Rossby modes with a wider meridional structure are significantly slower, and that changes how quickly you get the reflection at the western boundary. So is that okay? Okay, so then we talked a little bit about this response to anomalous convection associated with the El Nino. So this anomalous convection drives global atmospheric circulation anomalies. And so this convection will lead to positive height anomalies along the equator, which get communicated very quickly by atmospheric Kelvin waves. From west to east, the signal will propagate all the way around, so we'll see a figure of this. There will also be what are known as quasi-stationary Rossby waves that will propagate meridionally away from the equator and eastward. And so the most famous of these is known as the Pacific North American pattern, and this is why, for instance, California and the southeastern U.S. are strongly connected to El Nino because of this stationary Rossby wave propagation. And these dynamic and thermodynamic anomalies that are being driven in the upper atmosphere will affect the precipitation, including places like the Indian monsoon, as well as the near-surface air temperature. This will also modify the Hadley circulation. An important point is that at one time, you know, El Nino and La Nina are just opposite signs of the SST anomaly in the central and eastern Pacific, but they're not symmetric. The response is not symmetric either. There are some important differences. And I'll just show a couple of figures. One is this famous paper that people may have heard of by Ropoleski and Halpert, which talks about the global teleconnections, and the other one is by Goddard and Mason, which puts it into probability space. So here's 1983, January, February, March average. The contours are geopotential height anomalies. The shading is the precipitation anomalies. So you see that during the El Nino, there's increased precipitation in the central and eastern Pacific, decreased precipitation over here in the west. And the height anomalies, again, here's this zonal mean response along the equator. What is the height anomaly? So if you go up in the atmosphere, right, so if you integrate over the depth of the atmosphere, this is to 200 millibars. This is an indication of how the mass field has changed. Does that make sense? No. Oh, no, what an anomaly is. Oh, I'm sorry. Yeah, so that's the difference from a climatology. Yeah. That was okay? Yeah. And so this is again for a La Nina event, January, February, March 1989. And so again, you see that there's decreased precipitation here in the central and eastern Pacific, and somewhat of an increase here in the west. And again, this time you have a zonal mean response that's negative. You again see this wave type pattern. If you remove the zonal mean, the wave characteristic of this would be more prevalent. And this is the so-called Pacific North American pattern. There's some so-called also wave trains here in the southern hemisphere. But what you see is that it's influencing the atmosphere globally, including here over India. Obviously, it's not as important for your climate in January, February, March as it is in the summer. But yeah, not any rain, yeah, but it will certainly affect the winds over India. Yeah. Yeah, so again, here's just what the wind response looks like. So you see this circulation anomalies in the wind, and This, for instance, during El Nino, you see this strong onshore flow near California. This is why we get rain, excess rain during El Nino, and away from California. This is why we get not very much rain or dry conditions during La Nina. Okay, so here's this teleconnections. So if I say teleconnections, do people have some understanding what that is? It's not just the fact that you're forcing some response here and it's connected to other points around the globe. Yeah. So here's the standard Ropolesky helper for El Nino. Here's for La Nina. So again, you see during El Nino you get this wet, warm conditions here, very dry over northeastern Brazil, warm and wet over southeastern South America. And one of the issues with this is that this is very symmetric. But this was done by Ropolesky and Halpert in the mid-'80s. There was not a lot of data, especially there was no satellite data. And so more recent studies, like this one by Goddard and Mason, which actually shows the same sort of thing in a probabilistic sense for about 5 decades. I think they did this from about 1950 to 2000. You see the same sort of thing, during El Nino, it's tendency to be dry. During La Nina, tendency to be, I guess this is tendency of above normal, right? So tendency above normal, so it tends to be dry over southern Africa and wet during La Nina. And both of these studies are published, so you can actually look those up. But you can also see, as I had mentioned before, that it's asymmetric, right? I mean, there's certainly some places where you have a coherent signal that's opposite, low probability in one case, high probability in another. But there are other places where it's not. Okay, so then, soil moisture effect on seasonal climate. So most people would argue these days that after tropical SST anomalies, so not just the El Nino, but also Indian Ocean dipole and this north-south Atlantic mode, the soil moisture anomalies are considered to be important for driving the seasonal climate anomalies. But realizing that predictive skill is problematic because there are very few observations of soil moisture. So again, this is a place where data assimilation could play a role by helping to do a better job initializing the models. Yeah, sorry, there shouldn't be capital, right? And again, the records they do have for soil moisture that, in addition to being point sources, they're usually for not very long, 1 or 2 years, whereas the seasonal forecasting problem, we really want to have on the order of 30 years of data to be able to establish somewhat stable anomalies. Yeah, so most of the older land surface models actually don't initialize soil moisture with an assimilation system. They just drive the land surface model offline with observed precipitation and radiation to get the soil moisture anomalies. This has the advantage that the state that is produced is in good balance with the model, has very little observational data except for the surface fluxes. So again, this more formal data assimilation approach to assimilating these sparse observations is an area of active interest and research, especially in NASA. NASA and the U.S. Weather Service is doing it as well. Similar efforts in Europe. So what I'll show is a comparison experiment on the impacts of correctly initializing the soil moisture. So there's an experiment that was called Glacé that took, on the order of 10 different coupled general circulation models and initialized the soil moisture, let's call it correctly, and then with some random state, and then determine what's the difference in forecast skill. So perturbation experiment, and there was a second version of this called Glacé 2, and those are the results I'll show, which give some indication of the skill improvement for initializing the soil moisture. So again, the goal of this Glacé 2 project is to determine the degree to which the realistic land surface soil moisture initialization, and again, realistic, well, maybe, contributes to forecast skill of the rainfall and temperature at 1 and 2 month leads. So very short-term lead, and part of the reason for that is that if you go out, say, for 3 or 4 month lead, there's no impact. And again, it's using what at that time, this is about a 2 or 3 year old study, is a wide variety of state-of-the-art forecast systems. Okay, so here again, this is the way the initialization was done for the model. So there's observed precipitation, observed radiation, wind speed, humidity from reanalysis. again, which is produced by a data assimilation product, and it feeds into the land surface model. And then they get this initial condition to run these forecasts. So again, I think I had noticed these slides. Some of these slides will come from other people. This is from Randy Koster, who's from NASA Goddard Space Flight Center, who is organized this experiment for the Clive. Okay, so these are 6 different models, and what's being shown here is the difference in explained variance to correlation score squared from the case where you initialize the soil moisture correctly versus when you don't. This is for air temperature, and this is shown over the U.S. Many of the groups were from the U.S., as you can see, and also this is one of the places where soil moisture initialization has more impact than other places. But even there, you can see that it's not a tremendous impact. I mean, it's certainly not over the whole continental U.S. On the other hand, you know, depending on which model, there are some places where there's significant coverage. There are also some models where it doesn't improve things at all. So here's a comparison of a coupled model versus a model forced with observed SST. And this is for the air temperature for the second 2 weeks of a month, so a fairly short-term forecast. And so here's a comparison. This is the ensemble mean. I'll talk a little bit about tomorrow. Given the fact that seasonal forecast skill is a marginal problem, it's quite common to make multi-model ensemble means. The theory or the hope there is that the models have canceling errors and the strengths from one model show out while the errors from the different models cancel out. And that seems to have hold up to be true in various metrics and in various experiments over the last 10 years or so. So on the left is temperature. This is the averaging period for the forecast. On the right is precipitation. And so Randy points out that the weaker models are averaged in with the stronger ones. So the point there being that if you actually selected just the stronger models, you could actually probably do better, although that's not always the case. So you see for temperature of the multi-model ensemble, it does, you know, some improvement on the order of, you know, 0.1, 0.15 in some regions over, you know, various fairly substantial regions of the United States, whereas precipitation results are much weaker, and you know, by the time you're out into the second part of the second month, it's not really improving very much at all. Okay, so here's for temperature forecast, and so what they then did is to say, well, what if we actually looked at stratifying things by how extreme the soil moisture anomalies are. So if you know it's very, very dry or very, very wet, starting off, and you just look at those cases, is there a chance that you do better in forecast skill? And so this is for temperature. This is dividing the initial soil moisture states into terciles. This is quintiles, so dividing by 5, and this is deciles, so you know, into 10 categories. And so it's true, right? And you see the same general pattern. And as you go to the more extreme soil moisture states, you do improve skill. You know, it's pretty marginal at the longer lead how much improvement there is. And again, this is different periods. You know, second part of the 2 weeks, second 2 weeks of the first month, first 2 weeks of the second month, and then the latter part of the second month. And this is by Randy Koster. The article appeared in Geophysical Research Letters. Yes. Yeah, so forecasts, so land initial conditions versus those without land initial conditions, yeah. So those are the ones that are randomly initialized. These are the ensemble mean, yeah. No, R squared stands for the explained variance. It's the correlation squared. Yeah. And so again, for precipitation, the results are weaker. This is June, July, August again. Condition the same way, terciles, quintiles, deciles. Again, for the short lead, you do see some improvement. And then, you know, for the longer leads, the improvement is less, and the skill region is generally less. So again, I mean, I think that the dominant point here is not that these are great forecasts, but that initializing the soil moisture improves the skill a little bit. And the problem is that seasonal forecasting, again, we'll talk about this a little tomorrow, is a marginal skill problem. So anything you can do to improve the skill is considered good. I mean, you know, the Indian monsoon, for instance, the seasonal forecast that you guys get for even all Indian monsoon rainfall is also a marginal skill problem. Yes? This is done using observed, but observed means that it comes from reanalysis, data sets to drive the model, but there's no physical soil moisture being ingested. So it's a commonality for the experiment. Now, people are starting to assimilate soil moisture, but the problem is the sparseness of the data and the length of the time record. Yes? No, it's done offline. The land surface model is initialized offline. You run the land surface model offline with the forcing, yeah. So it will get down to, so what he's asking is how deep the anomalies go. And so the anomalies will go as deep as water will percolate down into the column over that time period.
So all the layers are
They could be affected. It will depend upon how quickly the anomalies go down. But because they're running this offline for, 15 years, and I would guess that the whole soil column is initialized, but you know that the deeper layers don't affect the upper soil moisture balance except on very long time scales. Can you speak up or get the microphone? My hearing is really bad. Sorry.
Yes. How frequently you change your land surface information? In your
When they're doing this?
Yes, yes.
Yeah, so the standard period for the atmospheric reanalysis would be 6 hours, and so it's a 6-hour update of those fluxes that's linearly interpolated in the winds in between 6-hour periods.
Okay. Thank you.
Yeah. Okay, so then we'll talk briefly about this difference approaches to dynamical seasonal forecasts. So in order to do the dynamical seasonal forecast, and I appreciate that people, especially in the math community, use this differently than I'm doing here, so let me say about that. So in my community, if you say you're using a dynamical model, that means you're time-marching partial differential equations. The other approach would be a statistical approach in which there's no time marching. So the minimum system you would need would be an atmospheric general circulation model, which again is one of these sets of nonlinear partial differential equations, and you need some method to forecast the SST. Okay, and so there are two common approaches. One tier is what's called coupled models, and that will include some sort of an oceanic model. Could be an ocean general circulation model. There are other schemes you could use that are not ocean general circulation models, but again, it would be some time marching formulation. And then the other approach is two-tiered or uncoupled models. And so that would use some sort of an offline model. It could be a statistical model. It could be somebody else's dynamical model to predict the SST, and that's prescribed for the AGCM. So generally speaking, this will be in it for the same atmospheric model, or always speaking, this will be considerably computationally less expensive than this. So the question is this a good approximation to this? And here's my motherhood statement, because over the last, let's suppose, 5 years, it's really become quite dogmatic that a lot of people believe that the one-tier models are the only ones that can be used for seasonal forecasting, especially in places like the Indian Ocean because of the air-sea interaction. And a smaller part of the community, including me, and Salochana and colleagues at IISC, and their collaborators, and Arun Kumar, for instance, at CPC, ENSO, thinks that the two-tier approach still has some value, okay? And so from our philosophical viewpoint, at least from my philosophical viewpoint, ultimately with this marginal skill problem, you should take the skill where you can get it, because you can combine these things into a multi-model ensemble. And so, again, the real argument isn't made about whether coupling is important. We're not saying that coupling is not important at some time scale, but when is it important? For instance, weather forecast models are not coupling, and people aren't claiming they need to couple to get weather forecasting skill to improve, at least not yet. I mean, there may be contexts where that's true. So what I'm saying is that on the seasonal, especially suppose the first season, 3-month lead, 4-month lead, coupling is not tremendously important, although that doesn't mean that it can't be important in certain circumstances.
You can do a kind of a coupling in the second mode, right? And you presumably change the forcing for the OGCM at the end on the time scale which you think is relevant, right? Or are they completely, the OGCM is completely independent of what happens in the AGCM?
In this case, it is. It is completely independent, but what you're saying I'll actually describe in a second. You can do a perturbation of that to test the importance of coupling. And some of us have done that, and that's why I say that I don't think it's tremendously important, at least for the time scale I'm talking about. People who look at long-running free runs of coupled models, things like the IPCC, we go out at a year. Clearly you need to couple. But if you're looking at 3 or 4 months initialized from an assimilation system, I would say you don't, and I'll show you why I say that. Okay, so, both of these systems, and so I should say this, in the U.S. it's politically correct to talk about positive parts of things and not negative, but let me say that if I'm saying one is positive and I'm not saying the other is positive, you can take that as a negative, okay? So positive attributes of the different approaches to the seasonal forecasting. For the two-tiered systems, computationally inexpensive. You could have more accurate SST because you could get the SST forecast from more than one source, right? I can make a multi-model ensemble of forecasts from ECMWF, from IRI, from the Canadians. There's also no drift of the SST annual cycle, right? I'm going to take these anomalies. So I'm not going to, in this type of system, I'm not going to prescribe the total SST. I'm only going to take the anomaly part. So I make sure that I keep the climatology correct, okay? Which is not the case for this type of system. In this type of system, you'll get drift. We'll talk about drift tomorrow. The drift in these systems, even on the seasonal time scale, can be the same size as the interannual variability. So the error that you get is the same size as the signal you're trying to predict. Okay, so the thing about the one-tier systems, they're potentially more accurate representation of the physical interaction. And this is true both for transients and for the time mean. And the reason I say the transients is that you can show that the Madden-Julian oscillation, 30 to 60 day oscillation, also called the intraseasonal oscillation, does have a manifestation at the surface, in the ocean surface fields. How important is that is a different issue. Yes?
The second point, positive attributes of the second one.
Yes.
That, if you want to do pure forecast,
Yes.
how is that possible?
Okay, so sure. So I have a forecast model. Let's suppose I have a forecast model, an atmospheric model. Let's suppose IISC is running a coupled model, and they produce a coupled SST forecast. So I have to wait for them. I'm dependent on them. NCEP has one. ECMWF has one. When they have their forecast, I can then take them and use them. I can also make a statistical approach to SST forecasting. Is that okay? Okay, so again, here's an example of an effect, and I apologize. This is work done by Andy Robertson. So this is the effect of coupling on the simulated Indian summer monsoon. So what I have here is the same atmospheric model. Here's a directly coupled model, so that means it has no flux correction, has plenty of systematic error. Here's the same model that's uncoupled. This is forced with a different SST product. This is from Hugh Vandendoel, the statistical scheme. And these balls represent the size of the anomaly correlation. And this is actually a statistically corrected. So what's quite common in seasonal forecasting is the grid sizes are fairly large. Let's suppose they're on the order of 150 or 200 kilometers in each direction, east and west. And so you can statistically downscale that into a more useful product. And so what Andy has actually done here is construct a statistical forecast scheme that takes the monthly mean data and uses that with observed data actually from the Indian government, daily rainfall data, to make daily rainfall frequency maps. And these are important actually. So we actually are doing some agricultural work with some colleagues here in India, and things like the rainfall frequency, how long or how many dry spells versus how many wet spells you have, can be more important than the mean precipitation in some cases for some applications. Anyway, so what you see is that the distribution of skill is different. And so sure, the coupled model, and again, India is one of the places where coupling probably does help you, although it's not 100% better always than an uncoupled model. So these are the places where, these large balls, correlations 0.6, 0.7. The coupled model has a pretty good distribution of high skill, but there are places where the uncoupled model is better, down here in the south. And so, the argument that I'm making and that some others make is that why not use both of these? Why be dogmatic and not use this model just because it's uncoupled? And this actually is a pretty weak example. I apologize, but I didn't have a lot of results for India, so I wanted to show a few. But there are other places where the skill is much more equable, or this skill is higher and the multi-model skill is higher yet. Okay, so here's and this comes back to the question that Chris was asking a bit. So simple test for the importance of coupling, right? So you can run a set of coupled model forecasts, and you take the SST from these coupled model forecasts, put that into the atmospheric model, but don't put it in every time step. Okay, because if you took the same initial conditions and put it in at every time step with the same atmospheric model, you get the same answer, right? So what you want to do is give the model a chance to produce its own surface fluxes, its own response to the SST that could or could not be different than the coupled model. And then if you compare the uncoupled and the coupled models for fields that you care about, things like precipitation, near surface air temperature, oceanic surface fluxes, you can see where the differences are. And again, if you do this, part of the problem for the seasonal forecasting is that the people who do decadal forecasting and centennial forecasting, when they do this with free model runs, you see a huge difference. But again, NWP, you see no difference, and I'll show you that there's very little difference for at least the first season forecast. And again, this is the point that I'm trying to make here. And again, one issue is that they are apparently different and it has an effect over southeastern Asia. So those fluxes are different over the western Indian Ocean, over the Indian Ocean and western Pacific. But I think it's hard to argue that one solution is necessarily better than another, coming back again to that figure I just showed you of this precipitation skill over India. Okay, so here again, this is a graph of precipitation versus sea surface temperature, local correlation, and precipitation versus SST tendency for June, July, and August, initialized on 1st of May. On the left, sorry, this is incorrectly labeled. On the left are the coupled models. This is should be coupled. Top panel is the precipitation SST tendency. Bottom panel is precipitation SST. And on the right set of panels is the same, but it's the uncoupled case, right? And so if, in fact, these two systems were very different, then these figures should look very different. And so the point that I'm making and that other people have made, although people use different techniques to get there, Slochina and colleagues have a more sophisticated technique. But my argument is that these patterns are awfully similar over large parts of the world. Here over the Atlantic, and again, there are some differences over the Indian Ocean, and so how important they are, from my perspective, how important they are will be more or better tested by how different is the skill of the near surface air temperature and precipitation forecast over land, because ultimately that's what you care about. So again, here for precipitation and SST, you see again the same sort of thing, the pattern over the Pacific, highly similar. Atlantic, again, highly similar. Indian Ocean, some difference. How important? I don't think it's tremendously important. If you did the same sort of thing at a one-year lead, it would look quite different. Does that answer your question, Chris? Or Jim? Yeah. I'm sorry. Yeah. So this is wrong. I apologize. This should say coupled. Right. So this. So this is the top two are a comparison of precipitation and precipitation and SST tendency. This is for the coupled model. This is for the uncoupled model. Is that okay? And then this is precipitation SST correlation. So this is DSST D small t. That's the tendency. So that's the derivative in time first derivative in time? Yeah. So if you look at the equation, so precipitation could affect SST in a couple of ways, or be affected by SST in a couple of ways. So in general, if the SST is warmer, it will rain more, although there's a threshold issue. And the reason you look at the SST tendency is that if you have precipitation, you have clouds, and the SST tendency will be affected by that. Clear sky will be warmer, cloudy sky will be colder. So this is kind of how the atmosphere, or how the precipitation or the clouds associated with the precipitation is affecting the SST. This is how the SST is affecting the precipitation with a simultaneous relation. Does that make sense? Yeah. Yes. It's monthly SST. Yeah. Okay, so again, I think I've mentioned that this seasonal forecasting problem is marginal skill. You can see just how marginal from a single model. I should also point out, I'm looking at June, July, August, mostly to highlight the Indian region. So it turns out that, maybe I'll talk about this a little tomorrow, the highest forecast skill actually occurs in the Northern Hemisphere winter, and part of the reason for that is that the stronger jet streams lead to a stronger basic state that leads to more propagation of Rossby waves into the mid-latitudes, and I'm taking a biased view because I live in North America. But if you look at any sort of a metric of global forecast skill of near-surface air temperature or precipitation, you would see that the winter is much better than the summer. Anyway, so on the left, I apologize, I've changed notation here. This is the two-tier or uncoupled. Here's the one-tier coupled, and this is the integrated measure percentage of grid points with the skill score or correlation above a certain value. And so again, and this is a June, July, August, started 1st of May. So there's no trace of initial condition skill in this at this time scale. And so you see again, if you look over South America, skills are highly similar. Are they identical? No. And again, from a utilitarian viewpoint, the places where they're different are places where you could try to use a multi-model ensemble to increase skill. I think that the bottom line message is that it's hard to say one is better than another. You can see that by the integrated metric, and this is just for the tropics. It is true that the one-tier scores are higher, but that's usually in the really low correlation range. And it is also true that over India, that the one tier is better. And so let me say that I'm not saying that you shouldn't use coupled models. I use coupled models all the time. I'm just saying that you shouldn't reject uncoupled models if they have useful skill. And that unfortunately is the way that the community wants to go. So again, here's the same sort of thing for near surface air temperature. It's also called the 2-meter temperature. And again, you see that these curves basically lie on top of each other. The green is the one tier, the red is the 2-tier. And the distribution of skill is highly similar. Again, 100% the same, no. But again, that's an opportunity to use both sources of information. Difference over India, certainly the 1-tier or coupled has higher skill than the 2-tier. But again, so and I've said this a few times, and I'll probably say it several more times tomorrow. Seasonal forecasting is a marginal skill problem. So you see that here you're looking at correlations, and places where I'll say have high skill have correlations of 0.4, 0.5, 0.6. If you tell a weather forecaster that, they would say that's below usable skill. But because a lot of the applications that are using seasonal forecast are looking at this probabilistically, and other issues that I'm looking at a deterministic metric here, what we know is that from the time sampling we have, which is on the order of 30 years, if you're doing this probabilistically, if you have an anomaly correlation of on the order of 0.3, you have some small amount of information you can use. Obviously, you would like for it to be higher, but anything below 0.3, I would argue, is useless. Above 0.3, you have a chance, but it will depend upon things like trying to statistically correct the signal, downscaling, these sorts of things. Okay, so here's for dynamical models. You can organize a dynamical model into two parts, right? So there'll be the time derivative, there'll be the dynamical core, and then there'll be the physics. So today we'll talk a little bit about the dynamical core. So I would say that the dynamical core, and I will talk about this Lynn-Rood finite volume type of approach. Even the spectral model, which I'll seem to be a little bit negative on today, which I'm actually not. It does have a lot of issues. there's not a lot of improvement that you're getting on the seasonal time scale from changing the dynamical core. It's the physics, it's the subgrid scale parameterization where you're really going to improve things. And that's a place where you could do things with data assimilation like parameter estimation that could hopefully make things better because you're not directly observing a lot of these fields. You're not observing the latent heat in the atmosphere. You're having to derive it as a residual calculation. And these are just some of the different things that are parameterized. So there's some mixing horizontal and vertical, there's terrestrial and solar radiation, there's convection from deep clouds and shallow clouds. So planetary boundary layer, and again, then there's the other aspects of the cloud, such as the liquid water transport. What is? Oh, this is just a complicated way of expressing the physics. So just if you would please bear with me and just say, here's some dynamics, here's some physics. Yeah, so this, I mean, in this case, LA could be some damping, right? So that would have the correct form, dAdt is equal to minus LA, some linear damping.
So when you were saying that things are moving away from spectral methods, that's for the core part.
That, right, so that's for the core part. Yeah, that's where the answer is. Yeah, I mean, rain and these sorts of things. Yeah, so the thing about the spectral core, it's a spherical harmonic representation of the dynamics. It has an exact calculation of the horizontal derivative. So they kind of switched over from simple finite difference methods, let's suppose in the late 70s, early 80s, mostly for this property. At that time, people, believe it or not, were using simple things like centered finite differencing, non-flux conserving. In fact, I'll show a figure a little later that has that sort of differencing. But the physical parameterizations and the nonlinear dynamical products, which we don't get to today, we'll get to tomorrow, those are calculated in physical space, in grid space. So you're not calculating the effect of clouds in the spherical harmonic space. You're actually calculating that in a physical space. Problems with it are that it has a Gibbs phenomena associated with sharp gradients. I'll show some examples of that. You get some bizarre behavior that people have made various attempts to overcome, and some things like you get negative mountain heights over the ocean. First of all, you get mountain heights over the ocean because the topography gets spread, and then they're negative as well, and then you get negative moisture. Another aspect of it is that because it's not diffusive at all, you have to add in horizontal diffusion to keep the model stable. This phenomenon is called spectral blocking. Usually the way that the spectral core is implemented is semi-implicit, so it does have a CFL instability constraint. Again, but on the other hand, it's still used by many forecast centers, including ECMWF, JMA, NCEP, CMA, and given the long time that it takes to develop models, you're likely to see them keeping these spectral dynamical core models for at least the next 5 years. NCEP in particular, I had mentioned, has just come out with a brand new model, which actually is being installed here in India. They're not going to have another model for 4 or 5 years, I'm sure. Okay, so then there's this new approach, or newer approach, that's generally based on Van Leer methods. It's called the finite volume. So it employs the finite volume approach, or Van Leer approach, as opposed to finite difference. Has no Gibbs phenomenon, has some diffusion, but you know exactly what the diffusion is because you choose a curve fit when you design the finite volumes. It's generally implemented in an implicit way, so there's no stability constraint. So the time step is controlled by accuracy considerations, not stability considerations. And in the US, actually, this has become a dominant dynamical core at the big centers, mostly because of the fact that it's extremely conservative with respect to tracer transport, things like upper level moisture, chemical species, and aerosols. And for instance, Goddard, GFDL, and NCAR have all switched to finite volume. So there are 4 major centers in the US. These 3 and NCEP, these 3 have all gone. These 3 are not doing weather necessarily. They're doing the longer time scale, and so they've all gone into finite volume. I would guess that NCEP one day will go to a finite volume as well. The other thing is that the spectral dynamical cores do not scale very well on massively parallel architectures, whereas the finite volume does, and that will be a consideration going forward. Okay, so again, I think I've spoken to some of these points, but I'll just go over them again. Finite volume, how do these finite volume and the spectral compare? Finite volume is much more accurate for the tracer transport. I'll show explicit examples of this. It also tends to produce smaller scale phenomenon, which is good, right? I mean, one of the problems with GCMs is that the precipitation fields are much too broad, much too large scale. That's not always true. There are times when you get spurious small scales, but the real features you want to model are generally better. Frontal features are much better with the finite volume. And it also has less wavy artificial features. And I've mentioned this about the usual choice of time difference. Yes? Is that right? Okay. Yeah, fair enough. Fair enough, you're right. Okay, so here's a comparison of the finite volume versus simple finite difference. So the finite difference scheme, and this is, let's suppose this is a wave in the pressure field or the height field. You see the finite difference field will have a lot of wiggles and bumps. Produces a maxima that's above, and so this was the this square shape is the original waveform, and then this dotted solid dot curve is after some time of integration, and this is actually not a very long time of integration. And then so here's Lin Rude with a piecewise parabolic, and so you see that it is diffusive, right? I mean, it doesn't represent the whole area, but it also doesn't have these weird features that are bouncing up and down, and it will maintain this shape for a long time. As time goes on, we'll just produce more weird bumps in the finite difference case here. So, and again, the reason that they started to go to these is mostly for the longer term time scale, but most of these centers are not developing multiple models, and so the model that will be developed for Centennial will be the same model that they'll use for all time scales, although perhaps weather will take longer to adopt it. So this is some scatter plot of different nitrogen-based compounds. These are the relative concentrations, and this is what the profile looks like in observations for a particular time. And then if you actually apply some dynamical model to that and let it act on it for a little bit, this is the spectral method. So you see that it's widened this distribution quite a bit. There's quite a bit of mixing what's not real. But if you were to look at a Lin Rude or a Van Leer method, you see that, in fact, they maintain a very tight shape, and so there's very little artificial mixing. Okay, so then let's look at what happens when you take the orographic distribution and try to put it into your spectral model. So I have several problems. The first is it will smooth out maxima, create these negative values even for the positive definite fields, in particular the orography and the moisture. You can actually modify this with the spectral filtering by, you can actually modify the spectral representation. After you do the grid to spectral transform, you can see where the negatives are, try to refilter them, and put it over the ocean, and you produce the amplitude. So that's a problem with this type of representation. This is the actual difference. This is the scale. This is what you've changed. So that's the difference, this minus this. And then if you actually just, so I'm taking this, I'm just plotting this orography field, but I'm only plotting negative values. So you can see the fact that out here over the ocean you have, divots or holes over the ocean on the order of 100 meters deep. So it's about 20 of, I don't know, I think I just have the equations left. So we could punt those to tomorrow if you want. Or, I'm supposed to go to quarter of. 10 of, right? Is that okay? Are people okay? I'm not talking too fast. Oh, I could do it in 10. I'm sure I can do it in 10 minutes. These are the equations in motion for a particular atmosphere, but this is a fairly common representation. These are the momentum equations, thermodynamic. This is for liquid moisture. This is for liquid water. Sorry, this is for vapor moisture, liquid water. This is the formulation that comes out of the DKRZ, the German Weather Service. So this is a common set of equations that's used to represent the atmospheric motion, again, including the moisture variables. And one of them is the liquid moisture, so that's more sophisticated than some models. And K here is a horizontal diffusion operator. The P is a vertical diffusion operator. So what's commonly done is to take this system and convert this into a vorticity and divergence form, and that will be used for the spectral method. And so that looks like this. So you have a vorticity equation, and you have a divergence equation, and you should really ignore the PU and the PV. Those are just these vertical derivatives that are being carried, and they're being left in the wind form, which is not common actually. That's actually not the way it's done in that model. But you get these nonlinear product terms, right? So you have F plus zeta times this thing which is called the pseudo wind, and so this is the wind times the cosine of latitude. You do this for U and V so that they go to 0 at the pole. And this is the pressure gradient term here, mu is sine of phi. And so it's this set of equations that will be expanded in spherical harmonics. You can also define, for people who have a meteorological background, a stream function and a velocity potential. So psi is the stream function, chi is the velocity potential. So the zone of wind will be a function of the rotational part of the flow and the divergent part of the flow for both u and v. So the vorticity is just del squared psi, and the divergence is del squared chi. And the thing about this, the reason to do this form is that when we get into the spectral representation, you can represent these with Fourier series and associated Legendre polynomials, which are these series solutions. So these variables will be expanded in this way, and so you have the coefficient, you have an associated Legendre polynomial. This is the Fourier coefficient. So if you haven't seen associated Legendre polynomials, they look like this. They have some symmetry properties. They're orthonormal, so they have some nice mathematical properties. And that's how you can derive the equations, or the coefficients, sorry. And then it's just this Fourier series. And so the thing, though, is that, so this part of the dynamics, if you see this part of the dynamical core, you know, these dynamical cores, for the most part, have existed for a long time. The physics will, again, and these nonlinear terms also, sorry, these nonlinear terms, every term that's nonlinear here will be derived in grid point space, and then these derivatives, this 1 over 1 minus mu squared d by d lambda, and 1 by a d by d mu, these will be computed in spectral space so that the derivatives are accurate. But you'll actually do these products in the physical space. Otherwise, you would have to do what's called the interaction coefficient method, determining which waves interact with which waves, and that's actually very expensive. Well, it's more expensive than doing this other method. One time it was very expensive. Now you could do it, but you know it's easier to do these things in the grid point space. And again, these are you know, just relationships about how you get the different derivatives. Again, these series solutions. So you know, I put these in here mostly if people are actually interested in seeing what those look like. You won't have to derive these. I mean, these are all coded in the model, and there's no reason to change them. So I think that's it. Tomorrow we'll talk about some stuff associated with the physical parameterizations. We'll go into some of those equations, talk about the model bias, talk about ensemble methods if we have time. So I hope it was somewhat useful. So typical number of modes. So for, let me say that the model that's being installed or has been installed in India from CFS is on the order of 300. Yeah, so 300 waves. Yeah. Yeah, that's a good question. So I think that usually what's done is that you increase the resolution and you adjust the physics to get global statistics. Or if US model will be global statistics plus statistics over the US for near surface air temperature and precipitation. You know, plus other fields, make sure that you don't damage anything.
I got two different meanings of the term seasonal forecasting confused in my mind.
Okay. Okay, sorry about that.
No, it's not you.
Oh, it could be.
No, you're clarifying that thing. So one is that you're trying to forecast over a seasonal time scale.
Yeah.
And that sounds like what you're focusing on.
So you usually want to forecast over a 3-month mean, January, February, March.
So assume that you know everything, you're living at the beginning of that time.
Yeah.
And then you want to forecast over that. I mean, the other sense is, the other sense is forecasting seasonal variations over years ahead of time. Like, what's the monsoon season going to be like over the next, say, 5 years or something? And it seems like ENSO and things like that are more relevant to the latter point than the...
No, ENSO is more relevant to the current, right? So people will talk about, I can forecast ENSO in 2 years, right? So I'll show an example tomorrow of a modern set of ENSO forecasts. And what you'll see is that the guy showed the spaghetti plot earlier, I can't remember his name. You'll see that that's how ENSO forecasts go. Yeah, Eric. So the reality is that we can forecast SST variability maybe at 6-month lead with reasonable skill, useful skill. So what you're trying to forecast is this year's anomalies against the climatology from all other years.
But in what sense do you need to know the mechanism of ENSO to do for the prediction of 3 months into the future?
So you want to know the mechanism because you want to be able to improve the parts where we're weak, right? So for instance, these things I'm showing where you have these anomalies in the height field or thermocline field. So currently models have a very diffuse thermocline, so they don't represent that correctly. So that leads to problems with wave propagation. Also, the vertical mixing is wrong, and so if you don't have the correct structure of the subsurface, that will affect how the vertical mixing works. Does that make sense? Yeah. So I mean, I tend to be, I would say that I'm a realist. Other people might say that I'm a little on the pessimistic side. There are people there's a group in Japan who will tell you that they can forecast out to 2 years. But what they're doing is they're extremely, and again, I mean, they have some impressive skill, but I would say that their useful skill ends at 6 months. They smooth their results tremendously, and so they kind of have a very low amplitude signal that has some resemblance because, again, you do have this tendency for the oscillation to have a period. But you actually take their data and look at it like everybody else's, they can forecast to 6 months.
But I think, as you pointed out, there's an emphasis now in IPCC to consider decadal timescales.
Yeah, so they're looking at different things there, right? So the decadal signal, and I'm not going to talk about that. So the decadal signal, they're trying to look at slower modes of variability, and one of those slower modes is the thermohaline circulation, which affects North Atlantic SST, okay? And so the stuff that I'm showing is low skill would be very high skill for decadal. And so if you can look at or forecast how the North Atlantic SST is changing with some accuracy, you may be able to say something about how hurricanes are going to vary, for instance. But again, that would be very probabilistic, and it wouldn't be showing hurricane tracks or anything like that. It would be, at this time, it's not. I mean.
So I would, maybe you mentioned this during your talk, maybe I missed it. I was just trying to think in what, so the weather forecasting issue, one of the big issues is the data assimilation, which is the initial condition problem. What is needed to improve the seasonal forecast in this? I mean, you mentioned that data assimilation could be useful, but many of the things that you showed, you were mentioning that the initial condition variability is not really, it's gone after.
So let me clarify that. The initial condition in the atmosphere is gone, not in the ocean. So the ocean data assimilation is the important part, not the atmospheric assimilation. If you're looking at the first couple of weeks, the atmospheric assimilation is important. If you're looking at the seasonal time scale, the ocean assimilation is important. You know? Could you repeat that question? No, so what happens is you'll make a forecast, so for instance, for 6 months, and then the next month you'll make a new forecast from a new ocean assimilation system, a new ocean assimilation state, sorry. So this is a European approach, let me say this, but this is also the approach I follow, mostly because it's easiest. People will forecast from the first of the month, okay? And they'll do that every month. So every month you produce a 6 or 8 month forecast, right? Because you know that the forecast at 4-month lead is going to be better than an 8-month lead. However, if you had some useful information, so I'm trying to be somewhat optimistic, put out the forecast for 8 months. Now NCEP is different. NCEP is producing forecasts every day. Seasonal forecasts every day. Actually, that's not true. I apologize. They're producing monthly forecasts every day. 5 times a month, they produce clusters of 5 forecasts. So they'll produce, on the 1st of the month, they'll produce 5 forecasts, 5 ensemble members. On the 6th of the month, they'll produce another 5 forecast members, and so on and so on. And they're doing that so that they can hopefully capture what's called the intraseasonal variability, things like MJO, intraseasonal oscillation. And, you know, certainly if you're looking at a phenomenon that has a 2-week period and you're initializing once a month, you're not going to do as well as if you're time sampling much more frequently.
No, you asked. Sorry, I was supposed to ask a question. Amit has already asked that question.
Oh, I see. Of what you need.
Skills in
Say again, Robbie, I'm sorry.
the errors in the ocean state,
Yeah.
let's say, I mean, if you are looking at the kind of thing we talk of, the correlation skills that we talk of for atmosphere,
Right.
if you want to look at for an equivalent of that for the ocean using a coupled model, what are the kind of errors that we are talking of?
So I'll show the bias errors tomorrow, and then, you know, skill-wise, I could see if I can throw a map in tomorrow. So at 6 months lead, I can try to. All right, so at 6 month lead, I'll just use this as an example. At 6 month lead, you probably have correlations here for a single model, not for a multi-model. Multi-model will be maybe 20 to 30% better. You have correlations here in this region, you know, also coming down here somewhat, this wedge shape on the order of 0.6. Over here, you would have correlations significantly lower than that, 0.3, 0.4. North Atlantic, you might in certain seasons get 0.5, 0.6. And Western Indian Ocean and Eastern Indian Ocean and the regions associated with the dipole, 6 months you're probably not going to get 0.6. And certain times of the year you might get 0.4, 0.5. I'll try to bring a map tomorrow.
And let's say we are looking at the intra-seasonal forecasting. What kind of a model? I mean, it kind of falls in between the seasonal and the short term. Short term, you know that atmosphere models are pretty good, but of course the jury is still out on the seasonal prediction. What happens in the intra-seasonal? Would you say it should be coupled or it should be pure atmospheric, or it's again?
So I think it depends upon your philosophical bent. If you want to do research, I think that the coupling is interesting to look at. If you want to get seasonal forecast skill, the 2-week forecast skill, I don't think there's any evidence right now that coupling helps.
Maybe what time it's reconvening.
Yeah, so I guess I already did that, so just to re-emphasize, we'll meet between 8:30 to 8:45 to talk about the problems from today's tutorials. Yeah? Okay. For students, yes, sorry, yeah. I mean, if others want to come by, that's perfectly fine as well. So. And I guess the ISC shuttle, we didn't really reschedule it, so they will miss that discussion, unfortunately. I will try to see if I can. Okay, how many people from ISC would like to come earlier? Who's from ISC here? There's 1 or 2 I see. So okay.
Certain questions don't have any answer.
Yes, exactly. So,
Retain the question.
just say that that's what will happen.
You have two here. There's two and so.
You would like to come in here? No, I think it might be a little difficult logistically at this stage. So, yeah.